Hello students, welcome to All Force e-learning channel. This is K. Nageshwar Rao, your physics faculty. Today we are about to deal with session number 45, first year Neet physics session number 45. In the previous session we have started a relative motion concept and we have dealt with relative velocity. We have seen how the equation for relative velocity can be obtained. Relative velocity is what? Rate of change of relative displacement. Displacement of one vehicle with respect to another vehicle. If both are having different velocities, displacement of one object with respect to another object changes with the time, isn't it? That's what we call it as relative velocity. And we have written one equation also. What is that equation? If you are having two objects A and B, and if you wanted to know velocity of A with respect to B, how it can be written? VAB bar is equal to VA bar minus VB bar. This is what we have written yesterday. And if you wanted to find the magnitude, VAB bar mod is equal to under root VA square plus VB square minus 2VA VB cos theta. So this is what we have concluded with in the previous session. Based on theta value, you will have different values for this one. If theta is 0, it means both the objects are moving along the same direction. If that is the case, cos 0 is 1, then finally what you will have? VAB, magnitude of relative velocity of A with respect to B. You will have it as VA minus VB if both are traveling along the same direction, that is theta equal to 0 degree. If both are traveling in opposite directions, theta value is how much? 180 degree. If that is the situation, cos 180 is minus 1, minus into minus plus 1. So finally, magnitude of relative velocity of A with respect to B will be equal to how much? VA plus VB when theta is equal to 180 degree. So this is what conclusion we have drawn yesterday, isn't it? Even here objects can move at some angle with each other also. They can move at an angle equal to some 45 degree or 30 degree or 60 degree, isn't it? In that situation also you can talk about relative velocity of A with respect to B. Okay. If you observe this VAB bar, for example, if you write VB bar, VBA bar, how do you write? It is written as VB bar minus VA bar. So when you compare these two equations, one thing is obvious: VAB bar and VBA bar are not same. Velocity of B with respect to A and velocity of A with respect to B are not same. They are opposite to each other. They are in different directions. Probably magnitudes might be same in these two cases. Magnitude might be same, but what is the situation? Both are in opposite directions, and we have seen various examples. Several examples were quoted by me yesterday. So let us continue with a few other models connected with this one. Before that, I'd like to stress on one more point. Sometimes acceleration related data will also be given. So if you wanted to express this relative motion in terms of acceleration, how it can be expressed? Let us say two cars are moving. Okay, one car is moving with an acceleration equal to A subscript A, small A subscript capital A, and another car is having acceleration equal to A subscript B. Okay, so let us say you wanted to find out relative acceleration of car A with respect to car B. So it can be written as A subscript AB bar is equal to A subscript A bar minus A subscript B bar. That's how you can write. So this is what? Acceleration of car A with respect to car B. Relative acceleration of A with respect to car B. Similarly, if you wanted to write relative acceleration of car B with respect to car A, how it can be written? A subscript B bar minus A subscript A bar. Okay, so the same things, same cases, so theta equal to 0, theta equal to 180, all those cases will repeat again. So in terms of acceleration also you can talk about relative motion. In terms of velocity also you can talk about relative motion. Okay, so let us pick up one or two possible applications. For example, let us say two trains are moving. There are two tracks. Let us say this is one train. Okay, so let us say this is the train engine. Okay, this is let us say of length equal to L1. How much is the length of this train? First train, L1. Let us say there is one more train. So this is its engine. Let us say its length is equal to L2. let us say this train is moving with a velocity equal to v1 and this is moving with a velocity equal to v2. So this is the situation. Okay. See, if v2 is less than v1, will you expect this second train to cross the first one above? No, it is not possible. If v2 is less than v1. If v2 is greater than v1, yes, it can cross. Isn't it? It can cross. So let us assume that v2 is greater than v1. v2 is greater than v1. So what happens at some point of time, this train crosses. Remember children, crossing of one train by the other in the sense, it's not like, engine of this train, if it crosses the engine of the first train, you cannot say that the second train has crossed the first train. Let me repeat this again. If engine of second train has crossed the engine of a first train, you cannot say that second train has crossed the first train. You can say that second train has crossed the first train only when the tail also crosses the engine of the first train. So finally the position, if at all if this has crossed, the tail of this train should be here and the engine should be somewhere here. Okay. Okay. So meanwhile, what is happening when it is crossing? How much length? How much distance it has to cover? Relative distance. Relative displacement. How much relative displacement it has to cover? It has to cover a relative displacement equal to L1 plus L2. With what velocity it has to cross? This is, these two trains are traveling along the same direction. So velocity of this second train with respect to first train is how much? It will be equal to v2 minus v1, isn't it? Velocity of second train with respect to first train is how much? v2 bar minus v1 bar. In terms of magnitude, since both are along the same direction, theta is 0, so v21 can be written as v2 minus v1, isn't it? So this is the relative velocity of a second train with respect to the first train, and with this relative velocity it overtakes or it crosses the first train, and while crossing the first train, how much is the relative displacement covered? L1 plus L2. So if you wanted to find out time in which the second train crosses the first train, you can express the time like this. Time in which it crosses this first train is equal to relative displacement covered L1 plus L2 divided by what is the relative velocity? v2 minus v1. And this is when both are traveling along the same direction. Okay, so this is what? Time taken by the second train to cross the first train. Okay, that too when both are traveling along the same direction. When both are traveling along the same direction. What if both are traveling in opposite directions? See, it's our practical observation. Let us say you are sitting in this first train. Okay, I am sitting in the second train. When this second train is overtaking this first train, when it is crossing the first train, you see the second train, passing very slowly just beside your train. What if the second train is approaching your train? In a swift, very quickly it crosses the train, isn't it? So time taken to cross the train will be less if both are traveling in opposite direction, isn't it? So mathematically let us verify that. Okay, if the two trains are traveling in opposite direction, if both are traveling in opposite directions, in this case t will be equal to time taken to cross is equal to, again relative displacement is how much? L1 plus L2 divided by what about relative velocity if both are traveling in opposite directions. If theta is equal to 180 degree, relative velocity will be equal to how much? VA plus VB. So here what will be the relative velocity in this case? V1 plus V2. Now compare these two equations. I'll take here T1, I'll take it as T1, I'll take it as T2, or well, be confused. Let us keep it as it is. So T and T. So if you observe these two equations, in the denominator V1 plus V2, large value is there when compared to denominator over here. If denominator here it is small, T will be large. If here denominator is large, t will be small. So when trains are approaching each other, very quickly they cross each other, isn't it? So that's how you can make use of a relative velocity concept to deal with the these kind of applications. Let us deal with one more application. Now let us deal with one more application, one more model. Train and running boy. Train and running boy. The boy is running inside the train. Let us say this is the train. Okay, so let us say this is the engine. Let us say somewhere here a boy is there inside the train. The train is moving along this direction with a velocity equal to velocity of train with respect to ground, VTG bar. Okay, from somewhere on the ground I am observing the train. So what do I see? I see velocity of train with respect to ground. We take ground as a reference because ground is at rest position. This is one thing which is known to us as a body at rest position. But in fact, Earth is also in rotatory motion. It is also not at rest position. When you observe from the outer space, from the moon, if you are observing the Earth is in rotatory motion, isn't it? So in this universe, absolute rest is not possible. For whatever things we observe on the Earth, we can take Earth as a reference and we can study everything. So with respect to Earth, with respect to ground, the train is moving with a velocity equal to how much? Some v bar tg. Okay. Let us say the boy is having a velocity equal to vbt bar. Velocity of boy with respect to train. Let me write it separately. What is the first one? VTG is velocity of train with respect to ground. Okay, velocity of boy with respect to train, VBT bar. Velocity of boy with respect to train. Okay, and the other one is velocity of boy with respect to ground, VBG bar. Velocity of boy with respect to ground. So here let us try to understand the situation. Let us say a train is moving like this in this direction. If the boy is also running along the same direction inside the train, okay, inside a bogie, he is running from one corner of the bogie to the other corner. Along the direction of motion of the train, he is running. What do you see from outside? If at all, if boy is at rest position, you see the boy moving with the same velocity as that of velocity of train, isn't it? If boy is running along the direction of the train, you see boy moving with more velocity. More velocity in the sense, already the train was having some velocity. On that, he is moving with some velocity. So both the velocities gets added. That's what velocity you see, you experience, with the boy. Okay. If the boy is running in the opposite direction, then the velocity of boy will be what? It will be velocity of boy with respect to ground. It will be difference between VTG and VBT. Why? Because he is running in the opposite direction. Okay. Remember, students, if the boy is running outside the train along the same direction, situation will be different if you are talking about relative velocity. If both the bodies are, if two cars are moving along the same direction, what did we take earlier? Velocity of one car with respect to other car is taken as, difference between the velocities, isn't it? If both the cars are moving in opposite direction, velocity of one car with respect to another car was taken as, sum of both the velocities. But here the situation is different. Boy is not running beside the train, he is running inside the train. Train is already in motion, and on that moving platform he is also running. So when both are, boy is running along the direction of the train, the boy's velocity will be, if boy is running along the direction of motion of train, so velocity of boy with respect to ground will be, okay, somewhere here one person is standing and he is observing the boy. Okay, so velocity of boy with respect to ground will be velocity of train with respect to ground plus velocity of boy with respect to train. So that's what velocity of boy with respect to ground. If boy is running in the opposite direction, if the boy is running in the opposite direction, opposite direction in the sense opposite to direction of motion of train. In that case, velocity of boy with respect to ground will be velocity of boy with respect to train minus velocity of train with respect to ground. So that's how you can write. Okay. So this is how you are supposed to handle. Okay. So let us deal with a few more applications connected with this relative motion. Now let us try to understand this model. Here one escalator is considered. Let the length of this escalator is equal to, I will take this length as L. How much is the length of the escalator? L. So escalator, you know, when it moves, what happens? It carries us to the top. You know, if I stand here, the escalator moves such that I will be here after some time, isn't it? So during that time, how much distance I might have covered? I might have covered the distance equal to L, equal to length of the escalator. Is that right? So here let us understand the situation. What he is talking about? A person walks up a stationary escalator in time t1. So the person is walking up a stationary escalator. The escalator is not in motion, it is at rest position, and on that escalator he has walked in a time equal to how much? t1. So in a time equal to t1, how much distance he has traveled? He has traveled a distance equal to length of the escalator, isn't it? Therefore, velocity of man with respect to escalator, it can be written as total distance covered divided by in how much time he has covered this distance L? T1 time. So what is this? Velocity of man with respect to escalator. Okay. And next, what he is talking about? Then, see, if he remains stationary on the escalator, then it can take him up in time t2. Let us say the escalator is moving and he is standing on the escalator. In how much time he will be taken up on the escalator? In a time equal to t2. In the previous case, the escalator is at rest position and he is walking. He is walking with whatever usual speed he can maintain. With that speed, he has walked up the escalator. And in how much time he has walked? In a time equal to t1. Since length of this escalator is known to us, can't we find the speed of the man with respect to escalator? Yes. This is equal to how much? L by t1. Now the escalator is moving and he is just standing on the escalator. In how much time he was taken up by this escalator, moving escalator? In a time equal to t2. So now what you can write? You can identify velocity of escalator with respect to ground. With respect to ground, how much it will be? Okay, in a time t2, let us say if you focus on this step. In a time t2, this step will cover a distance equal to L. It means it has come here. It has come here. So velocity of the escalator with respect to ground can be written as, again, length, or distance covered by this step of the escalator divided by in how much time it has moved up in a time equal to t2 seconds. So that's how you can write expression for velocity of escalator with respect to ground. Okay. See here also, when the person is walking up the escalator which is at rest position, here also you can talk about velocity of man with respect to ground, because if I am observing from the ground and the escalator is at rest position and a person is walking up the escalator, and whatever velocity I see, I can say that velocity of man with respect to ground, like that I can say. But here, when you are supposed to talk about velocity of escalator with respect to ground, there will be some contradiction. So very selectively it was chosen. So when the escalator is at rest position, whatever velocity the man has possessed, that velocity is expressed as velocity of man with respect to escalator. Okay, and when the man is at rest position and the escalator is moving, at that time escalator's velocity is taken with reference to ground. So velocity of escalator with respect to ground is how much? L by t2. Okay, so now what he is asking for, how much time it would take for him to walk up the moving escalator. Now the situation is what? Escalator is moving and person is also moving on the escalator. Sometimes we do the same thing when the escalator is in motion, we don't stand quietly. We too run on the escalator or we walk on the escalator, isn't it? So if that is the case, obviously the person will move up very quickly. He will reach this position very quickly. He will go to this position very quickly. We know that. Okay. So let us say I'll take that time as t. I will take that time as t. How much time would it take for him to walk up the moving escalator? I will take that time as t. And how that time t can be expressed? That time t can be expressed as how much distance he has to cover? He has to cover a distance equal to L only again, divided by what is the velocity? Escalator is moving and the person is also moving. Escalator is moving and person is moving on the escalator. Then the velocity will be like a train is moving and boy is also running along the same direction. So what is the velocity, relative velocity you have considered? You have considered, sum of both the velocities as relative velocity, isn't it? So here velocity of man with respect to escalator plus velocity of escalator with respect to ground. These two things you have to take. Okay. So now let us add these two things. What you will get? L by T1 plus L by T2. You can take out L common and it gets cancelled. So finally you are left with 1 by T1 plus 1 by T2. And if you take LCM, what you will get? Finally T1 T2 by T1 plus T2. So that's how you can find out time taken by the man to move up the moving escalator. Okay, the person is running on the moving escalator, the person is walking on the moving escalator. Okay, so let us deal with a few problems connected with this relative velocity. Now let us try to solve these two problems. The first one, a car starting from a point travels towards east with a velocity of 36 km/h. Another car starting from the same point. Let us say both have started from this origin. Okay, this is east direction, this is north direction. So the first car is traveling along east direction with a speed equal to 36 km/h. And the second car is traveling along north direction with a velocity equal to 24 km/h. So what we have to find out? We have to find out the relative velocity of one with respect to another car. So here he is not mentioning relative velocity of this car with respect to this one or relative velocity of this car with respect to this one. He did not mention. We can choose anything. Okay, so I will designate this car as car 1, this car as car 2. So relative velocity of car 1 with respect to 2. How it can be written? It can be written as V1 bar minus V2 bar. Isn't it? Or magnitude of relative velocity of first car with respect to second car can be written as under root V1 square plus V2 square minus 2 V1 V2 cos theta. Now tell me what is the angle between V1 and V2? It's 90 degree, isn't it? So cos 90 will be 0. So this term vanishes. And finally, magnitude of relative velocity of one car with respect to other car, you are left with V1 square plus V2 square. So let us substitute. What is V1 value here? 36 km/h. So 36 square plus V2 is what? It's 24 km/h. So 24 whole square. This can be modified like this. See, you can write this as 12 square into 3 square, isn't it? 12 3s are 36 plus 12 square into 2 square. So you can take out 12 square common. So out of the root, if you take out 12 square, you will have 12 under root 3 square, 9 plus 2 square, 4. 9 plus 4, 13. So 12 root 13 kmph is the magnitude of relative velocity of one car with respect to the other car. Okay. Now see this question, second one. A ship is moving due east with a velocity of 12 meter per second. A truck is moving across the ship with velocity 4 meter per second. A monkey is climbing the vertical pole mounted on the truck with a velocity of 3 meter per second. Find the velocity of a monkey as observed by the man on the shore. Let us say somebody is standing here on the shore and he is observing the monkey. Here the ship is in motion and across the ship, it means in a direction perpendicular to the direction of motion of the ship, truck is moving. Okay, and on the truck there is a pole and a monkey is climbing the pole. So when a man observes the monkey, what he sees the monkey moving along the direction of the ship with the velocity of the ship, and he sees the monkey moving along the direction of the truck with the velocity of the truck, and he also finds the velocity of monkey, in the upward direction. So in three different components of velocities we'll be able to observe when we observe the monkey from the shore. So let us try to write it in the form of equation. Velocity of monkey with